Okay, so here's our first section of exam 8, and we're going to talk about the idea of what we're going to call indefinite integrals, which you've really done already. No limits of integration, that's what's referred to as an indefinite integral, okay, right, which means we get r plus c. Limits of integration, that's called the definite integral, right, we get a number. So here this is an indefinite integral, right, the integral from f of x dx is capital F, the antiderivative plus a constant. The definite integral, you get a number, that's the exact area under the curve, okay? Indefinite, you just get a family of functions, that's what the plus c is for. It's essentially the first part of doing the definite, right? So this is the definite integral. You do the antiderivative, which we have here, evaluated from 0 to 2, you get 8/3. This would be an indefinite integral. You just do the antiderivative and add the plus c, right? It's a family of functions, it's very simple. So we've done this a lot. Now this one we talked about a little bit in that last section, if you recall as well, right? I gave you some bounds. I think it was -1 to 3, and 0 was included in there. It's not continuous. Fundamental theorem doesn't apply. However, you can do the indefinite integral, right? It's just the antiderivative plus c. This is just understood to mean that it only works, on the appropriate interval, right? So we're going to adhere to the convention that it's only valid if it's not 0. Obviously, otherwise the fundamental theorem doesn't work. So it's okay. You don't have to think about that. You don't have to mention it. I'm just mentioning that it's okay still to do the antiderivative or the indefinite integral. Table of indefinite integrals. This is exactly the same table as antiderivatives, right? No difference. We're just using a different symbol, the integration symbol. Don't forget the plus c, right? So this is all stuff you've seen before, right? All stuff you've seen before. So the integral of a rate of change is the net change, okay? In other words, integrating the derivative gives you the original function back, right? So integrating the derivative gives you the original function back. We can talk about that specifically with velocity, right? So given a velocity, can you find the distance traveled? Yes, because velocity is rate of change, and distance traveled, displacement really is net change. Now, notice that I'm asking to find the displacement as well as the distance traveled. Well, what's the difference? Displacement is just the change, the net change, right? It's the difference from where you end up as to where you started from. The distance traveled is the total. So if I start here and I go here and then back over here and then back over here and then back here, my displacement is 0. I started and ended at the same place. But obviously I've traveled a lot of distance. So here you just basically have to look at the absolute value. Okay. So the displacement is straight up net change, right? So you integrate from 1 to 4, the velocity. So the antiderivative here, given right there, from 4 to 1, a little bit of math here, and we get -9/2. So the particle ended up 4.5 meters, either to the left or the right, however you set it up, or down, whatever it is. But that's the displacement. Now, in order to find the total distance traveled, I have to see where it's positive and leave it alone, and see where it's negative and count it as positive. Okay. So here's our function, which factors into that. So notice that the velocity is negative from 1 to 3 and positive on 3 to 4. So the total distance is going to be 2 integrals. Okay, so from 1 to 4, I need the absolute value. So from 1 to 3, I have to negate it because it's negative. And then I have to add to that 3 to 4, which I leave alone because it's positive. Okay. So negating this function gives me this. Leaving the function alone gives me this. You do the 2 antiderivatives, add all of that up, and you'll get 61/6, which is obviously a lot larger than 9/2. Okay, so the distance traveled is greater. That's essentially, 1's pretty short here. So again, general antiderivatives shouldn't be a problem. We've done this already. Here, obviously, we have the fundamental theorem. Okay. Similar here with the homework, right? These are just general antiderivatives. Here I'm asking you to evaluate. These are definite integrals. These are area under the curves. Fundamental theorem part 2, you'll get numbers there. And then for these two, this is like the last example that we did. Displacement is just the net change, and then distance traveled, you have to figure out where it's negative and count it as positive.